So I'm going to talk about large-scale Bayesian inverse problems, which is something I've been working for a long time. But I'm going to talk about some iterative methods for large-scale problems, and in particular, I'll motivate the need for a generalized hybrid approach. So just to set some notation, this is quite similar to what Jim was talking about. So we have some data that we get from some experiment. It could be some tomography problem. And we assume that our forward operator is linear, but you can think of applying this in a nonlinear setting as well. And the parameters that we want to estimate are S, and the forward operator, or the parameter observation map, is typically either ill-conditioned or underdetermined. So you need to add some regularization to recover your solution. And we model the we model the noise as additive Gaussian noise, and we assume that the covariance matrix is a diagonal matrix. So, I mean, there's deterministic ways of solving it, but what does the Bayesian approach give us? So, it's a framework, it's a general framework for problems, but in linear inverse problems, it becomes something tractable. So, the posterior covariance density, it works in terms of distributions. So, the posterior density of the parameters given the data is proportional to the probability of the data given the observation, given the parameters, and some prior information about the parameters that you know. And in this case, if you assume that the prior is Gaussian, you can write down the exact distribution of the posterior, and this is also Gaussian. So the one thing I want to point out is that the choice of this Q can affect your solution, and I'm going to talk about what are the challenges associated with using this Q and how it can benefit us, and why we need special iterative methods. But the prototypical sort of application is something like image deblurring. So if you have an image like this and you have a blurring operator and you have noise in your measurements, and if you do something naive like invert the operator, you'll get something that is total garbage. But you add some regularization and you want to get something that's close to your true image, right? So, the basic outline of my talk is that I'm going to only focus on one mode of the posterior distribution. So this might be familiar to you. If you look at the negative log maximum of the negative log likelihood of the posterior distribution, it ends up being a weighted least squares problem. So again, there's a covariance matrix here, R, and there's a covariance matrix, Q. And it's this Q that sort of causes a lot of trouble. And in fact, there's an inverse, and we'll model the Q directly. So the main contributions of our talk are, we're going to talk about a hybrid approach for selecting this regularization parameter that can be quite expensive in practice. I also want to sort of emphasize like where we pick this Q coming from. So like we model this using Matérn covariance class of covariance family, and we show that this is a rich class, and this is really it's very flexible for changing the prior information. And so again, dealing with this Q, we'll need some special iterative solvers. And the main idea here is that we'll avoid forming the inverse and the square root of this covariance matrix. And since this is a Bayesian approach, you can derive uncertainty estimates and take samples from your distribution. But I won't focus on this talk, but you can take the like the ideas from this talk and do these things as well. Okay, so since these kinds of priors are very commonly used in geophysical problems, so I'll spend a little bit of time talking about how these prior information comes about. So for example, so we model the prior as a Gaussian random field, and we model this as a normal distribution with mean mu that's say specified, but you can estimate this in practice, and a covariance Q, and this, I'm going to spend some time talking about this Q. So the entries of this covariance matrix are given by the a covariance function, which I'll talk about a little later, and it depends on the distance of the 2 points in an image, right? So the farther these 2 points are, you want this covariance or this correlation structure to decay. So in practice, people take something like isotropic covariance kernels that depend only on the radial distance between these 2 points, and they depend on this correlation length. And in this talk, I'm going to assume that this length is known, but in practice, it can be estimated. So a couple of these popular kernels that are used in practice are these exponential. So the exponential depends on the radial distance between these 2 points and the correlation length. Or a Gaussian or a square exponential kernel, it's very similar except it uses R squared. Okay, so so the Matérn class of covariance family, covariance family is a very rich class of priors, and this is essentially the formula for the covariance kernel. It's an unwieldy formula, but it depends on two parameters, nu. Nu controls the differentiability of the stochastic process. So for example, we saw this exponential and Gaussian. They come up for special cases of nu equals a half, and nu equals infinity is the Gaussian kernel. Okay, so here's a plot of the covariance as a function of the radial distance, and as you can see, this covariance basically decays as r goes to infinity. But if you take samples from your distribution, so here I'm choosing 3 different values of nu going from a half, that's the exponential, and these are 2 different parameters of nu. And if you take samples from this distribution, you see, let's say for nu equals half, which is this blue curve, you can see that this process is quite rough. So suppose you wanted to reconstruct something like edges in your data, in your reconstruction, you might want to use a rougher prior. Or if you want something smooth, you can take like something like the Gaussian kernel, and this is infinitely differentiable, or something that's, that has only maybe 3 orders of derivatives. Many of you are used to looking at regularization in terms of the inverse of this covariance matrix, and this Matérn class has a very strong connection with regularization using differential operators. So it's not, there's not an exact formula, but for some values of nu and alpha, so alpha is the power of this exponential, of this Laplacian, so it's a fractional stochastic partial differential equation. And depending on the dimension and the differentiability of your prior that you use, there's some connection with these differential operators. So, I mean, people like using this for one reason. It's a sparse matrix and people can deal with it. But so as I've written this, the Gaussian priors are very difficult to use, and the reason is that the covariance matrix are dense because the correlation, we assume that the covariance doesn't decay until infinity, so it results in dense matrices. So if you do a naive approach on a million by million grid, this is completely infeasible. This requires about 8 terabytes in storage. So why would you want to use it? So well, this is an iterative method stock, and one only needs to deal with the covariance matrix times a vector, so an implicit matrix vector product, and the inverse. But let's assume I can do the inverse using a Krylov subspace method, but I don't want to do it. I want to avoid doing this. So the matrix vector product can be essentially accelerated. So for a dense matrix, you know that it would take about order n square operations. But for the image processing problems in which everything is on a regular grid, the covariance matrix has a very special structure. It is block toplets with toplets blocks, and so you can use FFT-based methods to accelerate the matrix vector computation. But on an unstructured grid, so for example, a finite element method, you could use something called the hierarchical matrix approach, which is similar to fast multiple method, if you've heard of this. So this is something that I worked on a lot during my PhD, and if you are interested in this, you can look at this paper. But the bottom line is, using both of these approaches, compared to the naive order n square approach, the storage cost is now n log n, which is, you can forget these factors of log, which are quite small. And the matrix vector cost is also n log n. So you can do, the advantage is that you can do what you would wanted to have done with the sparse differential operators, but you can do it in basically the same asymptotic cost. Okay, so I'm going to now focus on the iterative methods that I'm using to solve this, and I'll explain why there's an additional difficulty using the kind of covariance matrices that I do. So if you write down what the normal system of equations are, so you get A transpose R inverse A and lambda squared Q inverse. And if you see that, if I apply an iterative method to this equation right here, I have to form Q inverse at every iteration. Okay, I don't want to do that because it's expensive. But okay, so here's like almost a trivial observation. You make a change of variables. So you call x as Q inverse times S, and you subtract the mean from here. And similarly, from the data, you subtract the mean with the forward operator. And what you end up with is a transformed equation. Now I've got rid of the inverses here, and the Q appears here. Well, okay, so I've broken symmetry here. So this is a symmetric operator, and this is not a symmetric operator. But the observation is that this is symmetric with respect to a different inner product, the Q-weighted inner product. And that's the insight that I'm going to use. And you can also work out that this is the solution of this generalized least squares problem. So instead of a Q inverse here, now I have a Q here. But this is not exactly the normal system of equations. I need to add an additional Q to get the normal system. But the solution is equivalent. And if you know what prior conditioning is, this is a change of variables that is equivalent to prior conditioning, except we avoid these expensive square roots, which are almost impossible to do. Okay, so this is the main idea. Once you identify this transformation of variables, you can work out everything. As you know, for least squares problems, the Golub Kahan method is the thing that's very popularly used. And so, because we want to work with these weighted inner products, we derive something called a generalized Golub Kahan bidiagonalization. And there are many versions of this around as early as Benbow in '99, which is a one-sided orthogonalization. And these two are the ones that are closest to our work. But again, the advantage of our work or this work is that we avoid using inverses with Q. So if you recognize the Golub Kahan bidiagonalization, if you plug in Q equals the identity and R equals the identity, you get back your original system of equations. But the key difference is that now the U's and V's, which are the bases, are now orthogonal with respect to this inner product R inverse and Q. And the UK, BK, VK are related to the generalized SVD of A, and I'll explain that in a second. And you can work out what the Krylov subspace that is generated, and if you see that this is precisely the operator that I'm looking for here. And just as a reminder, the Krylov subspace is the span of powers of a matrix times a vector. Okay, so what are these generalized singular value? So we can show that these Golub Kahan bidiagonalization, if you take the UK, VK, BK, they're related to the generalized singular value decomposition. And what that is you can write this using a variational approach here. And so if I plug in R equals identity and Q equals the identity, this just becomes two norms. So this reduces to the definition of the singular values. But what you can show is this general singular values are the singular values of not A, but this transformed operator. And if you're a Bayesian, you will recognize this operator as a part of the prior preconditioned Hessian. And we can show that our Golub Kahan iterations, if you look at the singular values of that, they converge to the generalized singular values of A quite nicely. Okay, so then you have a generalized Golub Kahan. You can do a generalized LSQR. You can do a generalized LSMR. So you know what you can write the solution in the span of the subspace, and then you can search for an optimal solution in the subspace, and that boils down to a k by k least squares problem that you can solve very efficiently, and then you can reconstruct your solution. So a couple of observations that I want to make are that this is equivalent to running k steps of conjugate gradient with a weighted inner product. And like I said, we can use this to develop a generalized LSMR, but I won't discuss this here. So now I want to talk about the parameter estimation problem, and for this I'll use a hybrid approach. So to motivate this, estimating this parameter lambda is quite important in practice, and there are many different ways to do it. So some standard approaches, of course this is not exhaustive, that you can use, you can set lambda equals 0, and you can use an iterative solver and terminate it early to avoid semi-convergence. Or you could use one of these generalized cross-validation, discrepancy principle, and a slew of other methods to pick optimal parameters. But the problem with the second approach is that you have to solve many, many systems of equations. So a nice compromise is to use something called a hybrid approach. The idea is quite simple. You run an iterative algorithm for k steps, and then you project your original least squares problem onto this k-dimensional subspace, and then you add this regularization term, and then you can estimate this regularization term on a modified optimality condition. So for example, the generalized cross-validation and so on and so forth. So this enables automated parameter selection, but it also enables it in a way that is very fast. So I'll explain how we can use this for one particular modality, parameter selection process, which is called the generalized cross-validation. And we had to modify it slightly to account for these noise covariance matrices R and Q. And ideally, I wanted to call it generalized covariance cross-validation, but I thought it was a little too much. But anyway, the point here is that now there's an R inverse and R inverse here. And in a sense, this is related to the weighted GCV used by Julianne, Jim, and Diane. And this pseudo-inverse is now also has this prior information. But you can use the information from the generalized Golub Kahan to project this onto a k-dimensional subspace. And this is, if you recognize, this is very similar to what you would do with LSQR, but now the BK contains information about the generalized singular values. So it incorporates the noise and the prior information in these BK right here. And you can derive a similar approach for other parameter selection methods like UPRE and discrepancy principle. Okay, so the nice thing about hybrid methods is that there is some equivalence between running k steps of your algorithm, picking the best parameter lambda, or fixing the lambda ahead of time and running k steps of your method. Well, while we were not able to show this equivalence for the original problem because the Krylov subspaces generated are somewhat different, what we can instead show is that if we fix lambda equals 0 and solve this projected problem using the generalized least squares approach, and you form your solution in your original variables, this is exactly equivalent to running k steps of LSQR on the following Tikhonov problem. So the thing, again, you'll recognize this operator noise inverse a q to the half. So you can use your standard LSQR to run it on this problem, and this is a strong result because not only is it the transformation does not change the solution, right? But this is saying something stronger. At the end of k steps, you have exactly the same solution using both these approaches. In other words, you're getting in other words, you're getting away with not forming q to the half, but you're getting exactly the same solution, and the convergence is exactly the same. So some of you will also recognize that this is similar to the prior condition approach written in a slightly different way. Okay, so these are some very preliminary results, and mostly Julian is responsible for this coding. So the application is super resolution. So in many imaging modalities, you have to get a high resolution image, you take a bunch of low resolution images that are somewhat shifted or rotated in some manner, and you know exactly what these shifts are, let's say. And then you want to take a series of these observed images, and you want to construct a high resolution image. So this you can write this as an inverse problem as well. So in this first thing, plot, I'm going to compare our generalized approach with the LSQR with the covariance taken to be the identity matrix. So the dashed lines correspond to lambda equals 0, so there's no regularization, and you can see that there's some semi-convergence behavior. And what's interesting is that even with lambda equals 0, so essentially no regularization, you see some delayed semi-convergence. The error goes down a little bit. And the reason is that even though there's no regularization term, the prior information, because of the transformation of variables, the prior information is inherently present in our Krylov subspace method. So there's some regularization even without regularization, if you want to think about it. And these dashed lines the solid lines correspond to LSQR and generalized LSQR, and you can see that the generalized method is slightly different. It's slightly better than the LSQR approach. And I want to mention that we picked the optimal parameters, so we need to know the noise in advance. And if you look at the images, this is what they look like. You can't really tell the difference between these two images, but you can take my word for it that there's the relative error is lower. Okay. Now I'm going to compare different parameter selection methods. Again, solid line is generalized hybrid method with optimal parameter, and this is the best that you can hope to get. But of course, we don't know what the noise is. You can pick the optimal parameters, and the dashed line corresponds to the one with lambda equals 0, and we adapted our approach to different parameter selection techniques. The discrepancy principle, the generalized cross-validation, and the weighted generalized. So there's an additional omega parameter there. And we found that was the closest to the optimal parameter selection process. So you might be wondering what the effect of covariance kernels are. So I should mention that the previous examples were run with the exponential covariance kernel. So I chose the exponential covariance kernel again with two different correlation lengths. And I chose the Gaussian covariance kernel which is corresponding to nu equals infinity. And what we see is that in practice they perform quite well, and the best result was obtained by this exponential kernel with a relatively short correlation length. So if you look in images, The only thing you can see is it's slightly less grainy than the hybrid approach with just covariance equals the identity matrix. You can't really tell the difference between these three, but if in terms of relative error, this is the lowest. So in conclusion, we have this. I want to sort of say that this covariance family is a very rich class of priors. And I mean, the real advantage is that you can change your regularization by often changing only 2 lines of code. You only have to fix what your parameter nu is, and then you can get a whole range of regularization priors if you want. So we developed efficient solvers for solving these large-scale Bayesian inverse problems, in particular these 2 solvers, generalized LSQR and generalized LSMR. And the convergence of this can be understood by the analysis of the generalized SVD. And we developed a hybrid method for parameter selection that was particularly useful for this kind of covariance matrices. Anyway, and we show the equivalence to standard LSQR and prior conditional problem. So with this, I'm happy to take any questions. Thank you. Sven.
So on the very first or second slide, you said that your covariance noise,
yeah.
the R inverse, is a diagonal matrix.
That's right, yeah.
So I was wondering, how much do you lose by it? And could you make it more palatable by saying it's a diagonal plus a low rank term?
Yeah, I think we can definitely handle that. But I guess it's an issue of the modeling. If it's really uncorrelated, then that would be a good noise. But if you have some model discrepancy, then just a diagonal matrix may not be a good.
And so was it uncorrelated in these examples that you showed?
Yeah, they're uncorrelated. So yeah.
Question about the weighted GCB.
Yeah.
So as soon as you put in weighted GCB, you have yet another parameter.
That's right. That's right.
So did you choose that by hand, or did you have a scheme in the code where it chose the weighting for you?
Oh, I think yeah. So Julianne ran these codes, and I think she used the same strategy that you use for the omegas. Yeah.
So it had an automatic weighting.
That's right. Exactly.
Because as we go back to your convergence curves for that one. So you have, right, so the blue has weighted, so it does a little bit better, right?
That's right.
Not quite up to optimal, but maybe if you had a better way of choosing the weighting parameter, you might be able to get down to optimal or something.
Yeah, my feeling is that we can, in essence, we can model the noise as unknown except up to some parameter omega. So the parameter omega would show up both in this guy up here and this up here. So that might give better results, but we weren't able to.
Okay, any other questions? Okay, thanks again.
Thank you.